All right, time now for the last official lesson of Unit 2. This one deals with the derivatives of exponential and logarithmic functions. Again, the Unit 2 is a unit on differentiation. It's a unit on how we crank out derivatives. And so today we get to visit two of our old friends, exponential and logarithmic functions. That's the great hope, and that's what we're going to do. So, stuff you know from our work last year. And if you're just following us on YouTube, last year for these students would have been a course in IB Mathematics Standard Level, and it does cover some basic calculus. And so they learned last year that the derivative of e to the x with respect to x is e to the x. The actual proof of that comes from definition of derivative. It involves some stuff that's really nuanced. And so we're going to avoid a formal proof. I will, however, give you a nice graphical argument. So here's my e to the x. We'll take a look at that on some window that's a little bit more deal-withable. Maybe -5 to 5. There we go. And so we take a picture because it lasts longer. That's right. That's right. And so what ends up happening? I want to take the slope of a tangent line at that point, and sure enough, the slope of the tangent at that point is 1, which happens to be e to the 0. And then I go to take the slope of the tangent at x equals 1, and I get 2.71828. Wait a minute, that's e to the 1. And so we quickly recognize that at every point, the slope of the tangent line appears to be the actual function value. In fact, we can confirm that by doing a numerical derivative of e to the x with respect to x at the point x. And I'm going to make it bold so that you can see it pop up. Look at that. It's the same graph. The derivative graph is the same graph. I suppose these should switch places. No. So y is e to the x, and y prime is e to the x. So that's a well-established result. But what about other exponential functions? What about the derivative with respect to x of a to the x? Well, the derivative with respect to x of a to the x depends on how we write a to the x. The derivative of a to the x is the derivative of e to the x times natural log of a. Because this can be rewritten as e to the ln of a to the x. It's that old power to a power game where those powers multiply. And since e to the ln of a is a to the x is e to the ln of a to e to the ln of a to the x is e to the x times ln of a. That's the way I want to take the derivative, because the derivative of e to the x times ln of a, well, that's chain rule. How do I do chain rule? The derivative of e to the whatever is e to the whatever times the derivative of whatever. And whatever is a number times x. So what is that? The derivative of number times x is number. And then we get it into a familiar form. The derivative of a to the x includes a to the x. times ln of a. As a generalization, e to the x also follows that pattern, because the derivative of e to the x is e to the x times the ln of e. And that's stuff we ought to pay attention to. Okay. So, practice. We will differentiate. What if f of x is x squared e to the x minus x e to the x? Gives me a chance to remember my product rule. The product rule is so much fun. It's 1 prime 2, and the derivative of prime 2 is the derivative of e to the x, that's e to the x, plus 2 prime 1, and the derivative of the x squared is 2x, minus. And then we've got product rule happening here. It's so much fun. It's 1 prime 2, and the derivative of e to the x is e to the x, plus 2 prime 1, and the derivative of x is just its slope, and that's 1. And so what ends up happening is we get e to the x. That factors out. I've got an x squared. I've got a plus 2x minus a 1x. That's plus an x. And I've got a 1 e to the x at the end, but that negative sign gets distributed. Oh, really? And that's negative 1. Similarly, I could take the derivative of 3 to the cosine x. How do I take the derivative of 3 to the cosine x? Well, the derivative of 3 to the whatever is 3 to the whatever ln 3. So the derivative of 3 to the cosine x is 3 to the cosine x ln 3 times by chain rule. Cosine x is not x, it's a function of x. So we multiply by the derivative of cosine x, and that's negative sine x. So what have I got? I've got 3 to the whatever times ln of 3 times the derivative of whatever. Nice opportunities to practice product rule, to practice chain rule, just with some new creatures in the mix. Awesome. Well, the other thing we picked up last year in IB Math Standard Level is that the derivative with respect to x of ln of x is 1 over x. And I don't need a graphical argument for this one. We can prove this. We can absolutely prove this, and so I will. If I'm dealing with y is ln of x, right, y is the natural log of x, then x is the natural log of, no it's not. No, it's not. Silly. X is e to the y. X is e to the y. That's what the ln definition implies. And if that's the case, then I can take the derivative of both sides with respect to x. The derivative of x is 1. The derivative of e to the y is e to the y times dy dx. Chain rule coming up again and again. So what is dy dx? dy dx is 1 over e to the y, but we've already established that e to the y is x. And so we get the derivative just by using the derivative of the exponential function and a little implicit differentiation. As an aside, what about the derivative with respect to x of logs of some other base? Well, the derivative of logs of some other base, how do we rewrite? We rewrite using the change of base rule for logs. And the change of base rule for logs says that the log in some base I don't know is equal, oh my goodness sakes, is equal to the log of some base I do know divided by the log in that base that I do know of the base that I don't know. So if I can't work with log base 3, that's fine. I just convert that to a multiple of a log I do know about. And so the derivative of the log of x base a is the derivative of ln x, but that ln a is still in the denominator. The derivative of log x base a is 1 over x divided by log of a. Okay? Okay. So still playing everybody's favorite game, differentiate. What if I'm differentiating ln of 10 over x? Now, you should know that there are two ways to skin this cat. I will skin the cat over here using chain rule. Chain rule says that the derivative of ln of something is 1 over something times the derivative of that something. And that something is 10x to the negative 1. So the derivative of 10x to the negative 1 is negative 10x to the negative 2. And that simplifies. But you should also know that that can be skinned by rewriting the log function before we take a derivative. Quotient rule for logs says that, it should be the quotient property, it's not really quotient rule, that if I have the log of a quotient, I can just take the differences of the logs. Now that's very helpful because the derivative of ln 10 is 0, and the derivative of ln x is pretty easy, and we get the derivative that way. The College Board will, from time to time, throw up a question where you could do it by brute force, as in the green, but it's much easier if you use properties of exponents or properties of logs, as in the purple. All right, one more. J of x, x ln x minus x. I'm going to take a derivative. I'm going to take a derivative in orange. The product rule is so much fun. It's the first times the derivative of the second plus the second times the derivative of the first minus 1. Wait a minute. That's just ln x. Right, and that's all it's ever going to be. That's ln x. Everybody get excited. So again, we're in a unit on differentiation, which means we're looking to take derivatives of as many functions as we possibly can. And so you have to know how to do that mechanically. That's the goal of the unit. Can you mechanically take derivatives? And hopefully the answer is yes. So the next couple of days in class are just trying to cement these skills together. So this will be the last time that I talk with you in your own home before your exam, which I hope, by the way, goes very, very well. All right. Thanks, everybody.